Okay, so we are going to use the calculator and z-scores to make computations for percentile ranks in this video. So you should recall that a z-score is a ratio that can be used to determine how many standard deviations a value is from its mean. So a value from the mean, and this is a value minus the mean divided by the standard deviation. So that's my ratio. And the measure of center will always be the mean for these. And the z-score tells me how far I am away from the mean. All right, so it's relative to the variation or to the spread. So how far a value is from the mean relative to the spread. And we also said that z-scores can be calculated for any shape distribution. All right, so consequently, we can use it as a ruler to compare scores from different distributions. All right, so if we have someone who has a 1.2 standard deviations of the mean and someone else who has 1.8, we could say the 1.8 perform better, regardless of what the shape is and what the underlying distribution, regardless of sample size, we can make that comparison and make that claim. The 1.8 was higher than the 1.2. However, we can't use the empirical rule because unless they tell us that we're working with a normal. The empirical rule only applies to the normal distribution. So not all plus or minus 1 standard deviations are 68%. Only the normal. The plus or minus 2 standard deviations being 95 only applies to the normal. So the percentages that we work with only apply to the normal. So unless they tell us it's normal, there's not a whole lot we can do about it. But as it turned out, the students who scored 1.2 standard deviations and 1.8 standard deviations above the mean both come from normal populations, right? This is really a positive 1.2 and a positive 1.8. I know that because they say they were above. The fact that they came from a normal population is critical. If they hadn't, we couldn't have done what we needed to do. We could not have calculated the percentile rank. But since I know that they're normal, I can calculate the percentile rank. So with this said, here's what we know. Our population is normal. And I know that the mean is 0. And you're like, well, how do you know that? If they give you a z-score, put a big star by that. If they give you the z-score, if I give you a z-score, if that number is given to you, the mean will always be 0 and the standard deviation will always be 1 if we're working with a normal. Z-score for a normal is going to have a mean of 0, standard deviation of 1, always. They're telling us, hey, we converted it to the standard normal. All right. So first rule for the 1.2, it says draw the graph and label. All right. So here we go. We're going to draw a graph, and mine are never very pretty. There we go. Well, there's my mean of 0. And I know in this case that the student had a 1.2 or above. So this is what I'm looking for. Above means it's going to positive infinity. All right. So positive infinity is that way. But if we are actually looking for a percentile rank, so 1.2 and above would be this way. But since we're actually looking for a percentile rank, we need to do this. There are 1.2 standard deviations above. But we wanted a percentile rank, and percentile ranks always go from negative infinity. So how do you do this on the calculator? Very straightforward. Second vars, normal CDF. My lower bound. Basically, I shortcut this and I just load this up the full screen full of 9s. All right. Well, my upper bound was 1.2. My mean is 0. My standard deviation is 1. And once again, because they gave me a z-score and it's a normal, I know this is true. I press enter. And I was like, oh, 0.8849. So 0.8849. In other words, 88 about 88.5%. About at the 88.5 percentile. And we usually want to go 4 decimal places, so please keep that in mind. So here we have 1.8 standard deviations above. So if I'm drawing my picture, once again, this is above the mean. And we have 1.8, and we're wanting the percentile rank, so we have to go to negative infinity. So second vars, normal, CDF, negative 99999, that's what we use for infinity. So positive infinity, if they'd asked for it, we would have used positive 99. My upper bound, well, we stopped shading at 1.8. The mean for the standard normal is 0, because we're working with the z-score, and the standard deviation is 1. And we end up with 0.96. So 0.9640. All right, or about 96.4%. So that means 96.4% of the population is below this individual. All right, 88.5% is below that individual. So let's do some problems. All right, so we're going to do these with z-scores. So it says, compute the z-scores and calculate the probability. And so they're asking us to compute the z-scores. Well, if we're computing the z-score, then I know that the mean is 0 and the standard deviation is 1. This is the z-score. The life expectancy of a particular brand of light bulb is normally distributed. Really important. This tells me I can use the normal distribution probabilities for the normal part of the calculator with a mean of 1500 and a standard deviation of 75. So they're telling me, all right, the mean is 1500 and the standard deviation is 75. All right, so we know that information. What's the probability that a light bulb will last less than 1,410? So probability that X is less than 1,410. Well, here's my z-score. And basically what we're saying is we draw our picture. And we said the average is 1,500. Turns out 1,410 is below it. And we're going to go to negative infinity. Now, I know that's a theoretical negative infinity. The light bulb can't last less than 0 hours, but we still use negative infinity always. Okay, so we're not going to use 0. We'll use negative infinity, and there's my mean. So this is the area I'm interested in. Well, when I calculate that out, I'll take my calculator and I go 1410 minus 1,500. Divided by 75. So I end up getting a negative 1.2. Boom, right there. So now that I have that, I can go second vars, normal, CDF. We're going to negative infinity, and our upper bound we're saying is negative 1.2. Mean is 0, standard deviation of 1. 0.11506. So I probably should have truncated to be consistent. Now, one thing I wanted to tell you is I'm going to, in another video, I'll show you other ways to do things. You always have to give me the z-score. All right, you always have to give me the z-score. I know some of you are going, hey, can't I just do this? Can't I go second vars, normal CDF, lower bound, negative infinity, upper bound, 1410, and go, you know what? I'm going to put in the mean of 1,500 and the standard deviation is 75. And the answer is yes. You can do that, but I have to have this z-score. It's a requirement. I know it's a little bit silly, but this is something that College Board actually counts. You'll go from full credit to half credit just because you didn't show the z-score. Really important to show the z-score. The next one. So what is the probability that the light bulb will last more than 1,583 hours? So if I draw my picture, our mean is at 1,500. So our mean is here, and we go, oh, okay, we want 1,583 or more, right? By the way, this is facing the wrong way. This should be a greater than sign. So 1,583 minus 1,500 divided by 75. So 1,583 minus 1,500 divided by 75. And we end up getting 1.106. There we go. So how do I get that percentage? I go to second vars, normal CDF, and this time my lower bound would be this value right here. So 1.1067, and my upper bound is going to be positive infinity. So I'm just going to load it up with a bunch of nines. We're working with a z-score. So all z-scores have a mean of 0 and a standard deviation of 1. And there we get our 1342. Once again, had you wanted to, you could have gone second vars, normal CDF, and said 1,583 all the way to positive infinity, mean of 1,500, standard deviation of 75, and we get 1342. However, once again, I must have this z-score. That's a requirement, okay? So what's the probability it will last between 1,563 and 1,648? So probability that x is less, 1,563 is less than x is less than 1,648. So if I'm drawing a picture of this, our means here at 1,500, we're interested in 1,563 and 1,648. So I'm interested in the area of this shaded portion, right? I'm interested in that area right there. So I have to calculate two z-scores, and I always start with the largest first. So 1,648 minus 1,500 divided by 75, and I end up getting 1.973. Then I go do the lower one, 1,563 minus 1,500 divided by 75, and I get 0.84. So 1.973 and 0.84. These are z-scores, which means I have a mean equal to 0 and a standard deviation of 1. Second vars, normal CDF. Hopefully we can see all of that. And our lower bound, our lower z-score was 84 or 0.84, so 0.84. Our upper z-score was 1.973. Our mean z-score is 0, standard deviation is 1. And we get 1.762. And then you're going, hey, I know the calculator was doing upper and lower. Could I have done this directly? Yes, you can. So the second vars, normal CDF, lower bound 1,563, upper bound 1,648, mean of 1,500, standard deviation of 75, 1.762. But we have to have these z-scores. That's a requirement. All right. What's the probability to last between 1416 and 1677? Well, here's our mean at 1,500. 1416 is below it. 1677 is above it. So this is what we're looking for. Once again, I calculate the individual z-scores, 1677 minus the 1,500, divide by 75, 2.36. Okay, yeah, 2.36. I'm glad I have that right here because this off to the side is not correct. So this is going to be 2.36. And then 1416, 1416 minus 1416 minus the 1500 divided by the 75, and I end up getting negative 1.12. So I'm going from negative 1.12 to 2.36. Mean of 0, standard deviation of 1 because it's a z-score. Second vars, normal CDF, negative 1.12. Upper bound 2.36. Mean of 0 and standard deviation of 1. And I end up getting 0.8595, or 86% of the scores are between these values. All right. And once again, you always have to calculate the z-scores because I know some of you are going, hey, but I can go back and go second vars, normal, CDF, lower bound, 1416, upper bound, 1677, mean of zeros, mean of 1500, standard deviation 75. Those are actual values. Get the same score. All right, multiple choice test. You don't have to show me the z-scores, obviously. You can do it directly, but on a free response, I am going to have these z-scores because College Board will require them. All right, thank you.